This lecture is going to provide an introduction to cross-sectional evaluations within the context of highway safety. Okay, and so we'll start with a high-level overview and introduction to how cross-sectional evaluations are conducted from a methodological standpoint. And then we'll work through a nice simple example using some hypothetical crash data prior to a brief in-class demonstration of how we use SPSS, both for cross-sectional evaluations as well as for the purposes of conducting before and after and empirical based types of evaluations. Okay. On Thursday, we'll have a brief exam review from 9:30 to 10:30. The third homework assignment will be due this Sunday, and then we'll reconvene next Tuesday, March 30th, for the midterm exam, and that will be administered such that you have 24 hours to complete it, and that will be a mix of concepts and hands-on application projects similar to what we had done in CE 849. Okay. And so as we look at cross-sectional, or they're also referred to as comparative parallel studies, these are commonplace in highway safety in circumstances where we might not have access to both before and after data for a specific countermeasure of interest. And so as one example, if we look at things like signage or pavement markings or other treatments that are applied at large scale, and DOTs may have reasonably good records in their asset management inventory as to where these treatments have been applied, but typically information is more scarce in terms of when the treatments were applied. And so consequently, if we don't know when they were implemented, it makes it problematic when we're trying to conduct a before and after evaluation. And so as an alternative to that, a reasonable approach would be to compare locations where the treatment has been applied to other similar locations where that treatment has not been applied. And so if we think about this in concept, as compared to our prior examples where we had before and after period crash data for test sites, as well as potentially for control sites as well, in this case, we only have data from the post-installation period for where the treatment has been applied and for control sites where the treatment hasn't been applied. And so sticking with the same general terminology that has been introduced previously, in this case, the expected number of crashes in the after period after the treatment has been applied are simply obtained by direct observation. So we can measure how many crashes L occurred at the site where the treatment has been applied, and that provides us with an estimate of the parameter lambda. Okay. Now, if the treatment had not been applied, since we don't have before period data for these same locations, we instead are going to use the variable K here, which is just the count of crashes that occurred during that after period at the control site where the treatment had not been implemented. And so determining what the impacts of that treatment are, or the change or reduction in crashes, is just simply the ratio or the difference between pi minus lambda, so the number of crashes we saw at the sites without the treatment minus the number of crashes we saw at the site with the treatment applied. So that gives us an estimate of delta. And then our index of effectiveness, or our crash modification factor, then is just basically the ratio of lambda over pi, or the number of crashes with the treatment divided by the number of crashes without. So as you can see from that, it's basically analogous to the formula for crash modification factor, with a very small adjustment here. Basically, the larger the number of crashes in our control group, the more precision we have there. And so we would tend to adjust this quantity very slightly in those instances. As the sample sizes get smaller, this index of effectiveness will also tend to get smaller as a consequence of that if we have a relatively small number of crashes. But generally speaking, as our sample size gets larger, this will just converge towards lambda over pi. Okay. And so the setup is very similar to what we would have seen in just the simple before-after evaluation. Okay. And so in general, we have a 4-step process that we work through here. First and foremost, we need to estimate how many crashes we would expect to see during that after period, both with the treatment applied and with the treatment not applied. And so, as alluded to on the preceding slide, the number of crashes with the treatment is measured directly from those locations where it's actually been applied. And the without treatment estimate is going to be based on similar data for a series of control sites. Now, we'll want to be careful that these control sites are as similar in concept as possible, with the only principal difference being the treatment sites have that specific countermeasure or treatment of interest applied, and the control sites do not, but everything else is as closely matched as possible in terms of things like traffic volume, segment length, geometric characteristics, etc. Okay? And so if we have estimates of the expected number of crashes at both of those sets of locations based on empirical crash data, we know that crash data generally follow the Poisson distribution, and so the variance of those numbers of crashes are simply equal to the expected values, just given the nature of our Poisson distribution, and so that's determined directly from our data as well. And so under a Poisson distribution, the variance of crashes at the test sites is equal to the mean number of crashes at the test sites, and likewise, the variance of crashes at the control sites is simply equal to the mean number of crashes at the control sites as well. And so having established that, we can then estimate the changes in frequency, delta, as well as our index of effectiveness or our crash modification factor, theta, due to the treatment based on our estimates for lambda and pi. Okay, and so again, that differences in crashes is just our observed number of crashes at the control sites minus our observed number of crashes at the test sites. Likewise, our index of effectiveness, or CMF, is just the ratio of crashes at the test site over crashes at the control site, with the very small adjustment of 1 plus 1 over pi in this case, which will scale that CMF down slightly, with that scaling being slightly larger at smaller sample sizes. Okay. And then lastly, in step 4 here, we know based on our prior discussions about means and variances, for if we're adding or subtracting, so if we're taking sums or differences between two Poisson distributed variables or two random variables in general, the variance of that difference is going to be additive. So regardless if we're adding or subtracting these quantities, that variance term is additive. And in the case of the CMF, it's basically multiplicative. And so the variance of theta is going to be theta squared times this adjustment factor here, which is walking through this. We've established previously the variance of lambda is just equal to lambda. So this adjustment term is just 1 over lambda plus 1 over pi, similar to how we take our 1 over n1 and 1 over n2 in our parametric tests for sample sizes. And the denominator here is just 1 plus 1 over pi, that quantity squared, okay? And so we can use this then to estimate the variance of these quantities. We take the square root to obtain a standard deviation, and then we can construct 95% confidence intervals to evaluate whether these differences are significantly different from 0 in the case of an effect, or significantly different from 1 in the case of a CMF. All right, as we've seen in the prior examples, if we've had the treatment installed at multiple sites, or if we have multiple control sites, we know that those are basically additive, both the mean expected value of those variables as well as their corresponding variances. And so we can sum the number of crashes across locations, we can sum the variances across locations, and as those quantities get larger, we'll tend to see that it's easier for us to demonstrate statistically significant differences at various prescribed levels of confidence, okay? And so we'll return briefly to an example problem that was introduced previously. And so we had data for a sobriety checkpoint program. So we were given that a police district had previously experienced 150 crashes involving impaired driving, and that was reduced to 125 after the program was implemented. Now, if for some reason we may not have access to pre-implementation crash data, or maybe we don't know exactly when that program was launched, but we know since it's been launched in the last full calendar year, we had 125 crashes, okay? And so in the absence of before period data, the best way we could try to estimate how many crashes we would expect to see in the absence of that program would be to take data for a similar police district that simply hasn't implemented that program. And so in this case, we're given that another district has experienced 140 crashes during the same time period. And so based on that, we're able to then estimate what the impacts of the program would be in reducing crashes, okay? And so as outlined previously, with the treatment applied, our mean number of crashes is 125, and that's the same as our variance. At the control sites, we experienced 140 crashes, and so the variance of our crashes there is also expected to be 140. The effectiveness of the program, so we've basically seen a 15 crash reduction as we compare the test site to the control site. And the variance, again, being additive, would be 265. And so taking the square root, the standard deviation of that difference delta is 16.28. And so we take roughly 2 standard deviations to construct the 95% confidence interval. We'll notice here that that certainly overlaps with 0. And so while crashes have been reduced, we can't claim that that difference or that reduction is significant at 95% confidence, okay? And then similarly, in the case of our index of effectiveness or CMF, we're just taking the number of crashes with the treatment versus without, and then scaling that down slightly based on the sample size for the control group. And we see an index of effectiveness of 0.887, so roughly an 11.3% reduction in crashes. The variance of that quantity, again, is just 0.887 squared times 1 over 125 plus 1 over 140, all over 1 plus 1 over 140 squared. And so our variance of that quantity is 0.012. The standard deviation is 0.11. And so in this instance, our 95% confidence interval would range roughly from 0.66 to 1.10. Okay, so just taking 2 standard deviations. And since that range includes 1, in this case, we can't claim that there's a significant improvement. Likewise, to this case, the difference not being different from 0. Okay. All right. Related to this point, we've talked previously about the estimation of safety performance functions. And so the general form we see in this case, rather than working in a linear in parameters framework, we have crashes. Our mean number of crashes is exponential. So we can think about this. We're essentially logging our number of crashes to arrive at a right-hand side of the equation that's linear in nature. And since we're ultimately interested in the impact of variables on crashes rather than the log of crashes, we exponentiate the right-hand side here, okay? And so the general setup for intersections, we'll see this general functional form. So typically we'll have AADT on the major road and the minor road. We'll tend to log those, so these will become elasticities. And so in this case, we could actually pull these outside of the model, as we'll see on the subsequent slide. And these betas would tell us essentially for a 1% change in volume, what the corresponding change would be in crashes. And so if it's greater than 1.0, that would indicate we have an overly elastic effect. So we'd see at least a 1% increase in crashes for a 1% increase in volume. If those parameter estimates are less than 1, that would indicate we basically have increases at a decreasing rate. And so that could be reflective of traffic congestion. And so we see greater increases on the smaller range of traffic volume increases, and then those tend to become less pronounced at higher levels of volume. We can also account for the effects of other characteristics that describe those intersections. So the presence of a raised median or auxiliary right turn and left turn lanes, for example. And likewise, in the case of segments, we would log traffic volume. Similarly, we would also typically log our segment length. Now, we'll often treat this term as an offset, which means we would constrain this parameter to be equal to 1.0. And so what that means functionally is we would assume that if we double our segment length, we double our crashes. And there are various reasons why we would want to introduce that type of constraint. And then other variables that could be included, lane width, shoulder width, horizontal vertical curvature, those can also be accounted for by regressing
crashes against those specific variables. Okay. And so this next slide just demonstrates reinforcing the general functional form. So if we're actually logging those traffic volumes, they basically get pulled outside of the equation and they serve as multipliers then in that case. And consequently, in this circumstance, we'll generally find that we have better model fit if we log our volumes and lengths versus treating them explicitly as just our normal untransformed variables in those models. And so that's what we'll typically see in practice. And so when we go to interpret the effects of those variables, we're often interested in calculating what are referred to as elasticities. And so basically the average change in frequency associated with a change in any of those independent or predictor variables. And so if a variable is continuous, all we need to do is basically exponentiate those coefficients, and that would serve as similar to a crash modification factor. So if we exponentiate beta, that would be the ratio of how many crashes we'd expect to see with that treatment versus without the treatment, for example. We subtract 1 here, the exponential of 0, which would correspond to no effect, would be equal to 1. And so this would tell us the percent change we'd expect to see in crashes for a 1 unit increase in X, okay? And so a binary indicator variable would be a special case of that. And so if the variable is equal to 1, that beta tells us essentially what the increase in crashes would be as compared to the baseline condition where X is equal to 0 or that condition is not true, okay? We can also see continuous variables like lane width or shoulder width or whatever the case may be, where that elasticity would correspond to a 1 unit change. So a 1 foot increase in lane width or shoulder width as an example, okay? And then as alluded to on the preceding slide, if we log those X variables, we can then interpret that as an elasticity, which would basically mean for a 1% change in X, what's the corresponding percent change we'd see in Y, okay? And these are all demonstrated on this subsequent slide. So this is based upon a study we had conducted for the Michigan DOT earlier in around the 2010, 2013 range. So in this case, we had work zones that were installed at various sites throughout Michigan. And those work zones would have included either a shoulder closure, a single lane or double lane closure, or a lane shift where you basically have a divided highway and we close one direction of that highway and there's a shift so traffic moves over to the other side of the median, and you're running 2 directions of traffic on just one side of a divided facility, okay? And so what we've done in this model, we've compared those conditions and the periods during which those work zones were in place to the same segments 1 year prior. So we're basically taking the difference in the number of crashes under normal non-work zone conditions versus when any of these work zone scenarios were in place, okay? Now, as a part of that, we have 3 other variables of interest: the traffic volume at that site, the segment length, and then the duration of the analysis period. And that would be based upon what the duration of the construction projects were. And so obviously, if the project was in place for a month or a year or a day, those would have marked differences or impacts on crash rates. Likewise, if volumes are higher or the segments are longer, we would also expect to see increases in crashes there as well. And so we're controlling for these conditions. And you'll notice we've logged each of these parameters. So they're now pulled outside of the parentheses here, okay? And they're raised to the beta power since we've done a log transformation, okay? And as we look at the results here, we see, generally speaking, each of those continuous variables is roughly elastic. And so as we increase the duration of the project, a 1% increase in volume results, or a 1% increase in duration results in a 0.895 or roughly a 0.9% increase in crashes. Traffic volume is roughly elastic, so a 1% increase in volume leads to a 1.04% increase in crashes. And then segment length is somewhat inelastic. So a 1% increase in segment length results in a 0.83% increase in crashes. Okay. And then each of the different types of traffic control treatments is comprised of a series of 0, 1 indicator variables. And so we don't really see much of a difference in shoulder closure. There's a very marginal and not statistically significant change in crashes. But we do see pronounced increases in single or multi-lane closures. Interestingly, those are roughly the same order of magnitude. So whether we're closing one lane versus two or more, we see crashes increase from just under 20%. And in the case of a lane shift, those increases are even more pronounced. We see roughly a 70% increase in crashes in the case of the lane shift, okay? And so for the cross-sectional analyses, as well as for any of the empirical bays or before and after with control type analyses, we can use this same general approach to try to quantify what the effects of different treatments of interest would be, okay? And so that wraps up the lecture portion of today's course. As a reminder, exam review will occur this Thursday. Homework 3 is due Sunday, and then next Tuesday we'll have the midterm exam, okay? Okay, now at this point in time, I wanted to give a quick introduction to SPSS as it's used for the estimation of safety performance functions. And so that can be used directly for our analysis activities here. And so we'll just start with some very simple exercises here. So as opposed to the regression toolbox where we typically would run our linear regression models, for Poisson or negative binomial, we're going to work under the family of what are referred to as generalized linear models. And so under generalized linear models, we can select this option. And the setup here is can be used to estimate a wide range of different families of models, including linear models, logistic regression models. And of particular interest here are Poisson and negative binomial models. Now you'll notice we have these two options here. We also have a custom option I'll get to in a few minutes. But just to demonstrate how this works, we'll first of all estimate a Poisson model, okay? And so our dependent variable here is our target number of crashes that were experienced on these individual segments. And all I'm going to do here is I'm just going to estimate a model with only a constant term. So I'm not including any predictors. I'm going to hit OK. You'll see the indicator here that I'm estimating an intercept only model, and that's fine. That's my intent here. And so as we scroll through our results here, we'll see a model with a constant term, which is equal to 0.406. And so what does that number mean? Basically, if we exponentiate 0.406, that would give us the mean number of crashes we would see across that entire set of segments, okay? We will go back in and we can estimate that same general model structure, except in this case, we're going to use a negative binomial as opposed to a Poisson model. And so the only difference here is that we're introducing some additional variance beyond what is seen in the Poisson model, where we assume the means and variances of the counts are equal to one another. And so in this case, that 0.406 has remained the same. Interestingly, we now have an overdispersion parameter that's been set equal to 1.0, but by and large, no real differences of note here. The third example, and so you'll notice there, as I had mentioned, we've constrained alpha, or we've also seen that referred to as K in the highway safety manual. We've constrained that to be equal to 1, which isn't necessarily what we'd like to do here. And so we can also go under custom model, estimate a negative binomial with a log link function, which means we're logging our dependent variable, our y. And we can either specify a value, so we can set it equal to 1 as SPSS does as a default, or we can actually try to estimate alpha or K as a part of the model estimation process, okay? And so I'm going to do that again. And in this case, you'll notice not really any change in terms of that parameter estimate. We do see that our overdispersion parameter is actually increased from 1, and so it seems that there's even more variability Now, part of the reason for that is that we haven't included any of the other important predictors in our model at this point, okay? So the next thing we'll do is work through a few examples with slightly more complex models. And so I'm going to go back up under generalized linear models. In this case, I'm going to add some predictor variables, and specifically, I'm going to add AADT and segment length. I've not included the log form of these variables yet, but this is just to kind of demonstrate functionally how these models are working. After entering the response and predictor variables, we also need to drag these over to the modeling dialog box. If we don't, we'll get that error message that we're estimating an intercept only model. So just because we've added the predictors as shown on the preceding slide, that doesn't mean that they've actually been included in the model, okay? And so what I'm going to do then in this case is I'm going to add both of those variables into the model. I hit OK, and it will rerun our analysis. And now in this case, there are several marked and important differences here. So first of all, our intercept term has changed significantly. And part of the reason for that is we've included AADT and segment length in our models, okay? Now we've included these as non-transformed variables. So they're just in their natural form. And so this is actually too small to really even see what's happening here. But if we click on this, okay, and so as we look at these model results, we'll notice our intercept term has changed significantly, and that's because we've included some additional predictor variables, and that includes AADT. And so here we see that coefficient is very small. It's 0.000131. And so we can exponentiate that, and that would tell us the corresponding increase in crashes we'd see for a 1 unit increase in AADT. Likewise, segment length shows a parameter estimate of 0.242, so we can exponentiate that, and that will be a number that's roughly equal to 0.23, 0.24. And so that's telling us for a 1 mile increase in segment length, that would be the corresponding percent increase in crashes that we would tend to see as a result, consequently, okay? And the other thing that's happened here is our alpha, our over-dispersion parameter, has reduced significantly. So from 1.1 roughly, it's fallen all the way to 0.507, which means this is a better fitting model. Okay, now rather than just including AADT and segment length directly in the model, I'm now going to include the logs of both of those respected variables. Now keep in mind, I'll need to add both of these back in to our predictors. And now as we scroll down, we'll notice our results are slightly different. And so since we've logged these variables, these can be interpreted as elasticities, as I had alluded to previously. And so a 1% increase in traffic volume corresponds to roughly a 0.7% increase in crashes. And a 1% increase in segment length corresponds to roughly a 1%, or in this case, a 0.98% increase in crashes. And so based on this, it probably seems like a reasonable assumption that we would treat length as an offset term, okay? The other thing that's happened here, our over-dispersion parameter has been reduced significantly from greater than 1 to 0.255, which means this is a significantly better fitting model in this case, okay? And so I'm going to go back up real quick. And we can also, if we'd like, we can, as I had indicated, move that from a covariate to an offset. Our model output here looks quite similar. We see very marginal changes in our intercept and our log of AADT, and that over-dispersion parameter is virtually unchanged when we constrain that parameter estimate to be equal to 1 for segment length, okay? And we can basically continue working through these models. In the case of a cross-sectional analysis, we could assess the effects of different variables. So let's say lane width, if lanes are 10 or 11 feet in width, this is just an indicator variable. So I'll add that to my model in both cases here. Hit enter, and we'll see an increase. So if we exponentiate that 0.05, so roughly just over a 5% increase in crashes on 10 or 11 foot lanes as compared to 12 foot lanes. That's not quite statistically significant, but it looks like there may be an effect there. We can go through, and for other variables, we can add those to our model as well. And that would include looking at various combinations of centerline rumble strips, centerline and shoulder rumble strips, etc. And so our general process here would be to work through and use this model to estimate our safety performance functions, whether that's for the cross-sectional analysis or the before and after or the empirical Bayes type approaches, okay? Now, there are a few important aspects of the data set that should be described up front. So first of all, these rumble strips were installed over a 3-year analysis period, okay? And so in each case, for every segment, we basically removed the year in which the rumble strips were installed because we don't know if those were installed in March or September. And so working with partial years of data makes the analysis a bit more messy. And so we've zeroed out that year, and we've included 3 years immediately before installation and 3 years after installation of those rumble strips. And so as you look at this after variable, that's equal to 1 during the after or post installation period and 0 otherwise. The next 2 columns describe the nature of those segments. So if those segments are where centerline only rumble strips were installed, so basically in cases where the total pavement width and particularly the shoulder width was relatively small and there wasn't sufficient room to fit in both centerline and shoulders, only centerlines were installed. On the wider road segments, both centerline and shoulders were installed. But you'll notice here, we've assigned the same value to all 6 years of the analysis period here. So this doesn't mean that centerline rumble strips were installed on that segment in that given year. This just means that at any time during that period, centerline rumble strips were installed. And so for analysis purposes, you'd want to work with a combination of these variables to ascertain whether or not rumble strips were in place in any given year, and if so, whether those are centerline and shoulder or centerline only, okay? Outside of that, most of the other variables are rather straightforward in nature. For our analysis, we're purely focusing on the target number of crashes. And so to that end, we can conduct either a before-after analysis, a cross-sectional analysis, or an empirical Bayes analysis using these data sets, okay? Now, since there's not a natural control group in this case, because we've milled the rumble strips everywhere, I would encourage you to basically hold out a portion of the sample. So maybe there's 3 years of data. So you could take the 3rd year of installation and use that as your control group, for example. Or you could use your 2nd and 3rd year as control groups for the 1st year. But ideally, I'd like the same type of approach to be applied in each case. So you would compare crashes before and after using the naive method, and then using the cross-sectional method, and then lastly using the empirical Bayes method, okay? When you estimate the SPF for the empirical Bayes, you'll want to do that using the subset of sites where the rumble strips have not been installed. So again, whatever subset of years you decide to exclude as your control case should also be used for developing that SPF, okay? And so from there, it's relatively straightforward. You can either work through each of those methods from a regression framework, or you could simply look at changes in crashes as we had done in the example problems we've worked through on the PowerPoint slides previously. But either of those approaches would tend to give you similar results ultimately. And so this at least provides you with a very high level introduction. And if you have any further questions on any aspect, I guess just let me know. But otherwise, this should hopefully be enough to get you started, okay?